Hi, in this video I'm going to be presenting the benchmarking server used for benchmarking the ML performance of various devices. I'm going to start with an overview of the UI followed by an overview of the code. So the benchmarking tool is built in two parts. The first part is the benchmark.py. This will open a web UI in which you can choose the username, the IP address, the password of the system under test, the ONX file which you wish to benchmark and which should be converted to an intermediate representation, a validation dataset, the batch size, the precision, and the platform. Currently, NVIDIA and Intel's OpenVINO format are supported, but only NVIDIA implementation is fully tested. So, to give an example of how this works, I will be connecting to a laptop with this username. Its IP address is 113.0.113. The ONX file should be converted from a suitable format to the ONX file, which can be used for converting to other intermediate representations. This will be converted to TensorRT for NVIDIA and a bin file and an XML file in the case of OpenVINO. The validation dataset is used for checking the accuracy of the model, and the batch size is used for specifying the number of images which can be processed at once. Use FP16 for faster inference and FP32 for supposedly better accuracy. When you press the benchmark button, several things will take place. So I will show how that works. So this output over here is live streamed from the system under test. So this is actually std out of the system under test, and the first thing which it does is it will execute a test run of the TensorRT file. It will then show the time required for each line of code of the test script. Once that is done, it will be copying over the validation.zip file, which contains scripts required for validating the model. That includes the test images as well as the validation scripts, which will post-process the output of the neural network and then compare them with the ground truth. Once that is done, the validation is complete. In the second part of this project, I will now be showing the UI for viewing the benchmarking results. For that, run dashboard.py. This is using the Dash library, which is developed by Plotly, which is a Python library for data visualization. So this is actually what the UI looks like, and the first graph we see here is of each operation. So there are four operations we are benchmarking: the reshaping of the input tensor, the time required to copy to the GPU, the time for inference, as well as copy from the GPU. We are currently testing two platforms in this. We are testing the Jetson Nano, which has the identified Tegra ARC64, and the other system is the laptop equipped with an NVIDIA RTX 2060 GPU. So with this UI, you can filter which platform you wish to see the results of. For example, these are the results only for the gaming laptop, and this is the result for the Jetson Nano. The scales will change accordingly. So you can also filter by batch size. Currently we only tested for batch size of 1, but different sizes can be tested. And you can also filter by the floating point precision, either FP16 or FP32. The model accuracy and validation data is run by running the validation scripts, and we can see that we have done it for both the Jetson Nano as well as the RTX 2060. The model name is of the format of the ONX file name, followed by the floating point precision, followed by the batch size. So this is an overview of what the dashboard looks like for viewing the benchmarking results. So now I'll be walking through the code for both of these. I will be starting with the benchmarking tool, and we can see all the steps of how the data is copied and how the benchmark is run. So this benchmark.py just launches the CherryPy web server, and that is used for running all the other utilities. So from there we go to URL handler, which is actually just exposing the endpoints which are required, and the main thing which you should look at is the data endpoint, which takes all the details required and then sends these details to send and execute test. So in send and execute test, we first connect to the device under test, the system under test, by using the Paramiko library. We connect using SSH, and then we open an SFTP connection. And with the SFTP connection, we can copy our the ORNX file as well as the benchmarking scripts. So in copy ORNX file, we actually copy the ORNX file itself as well as all the scripts required for benchmarking, such as TRT inference, make TRT, convert and test TRT, and convert and test OpenVINO. So I'll be focusing on TRT in this presentation, but the same applies for OpenVINO as well. So once the ORNX file is copied, we then run the script over here. So this is the script which is run actually, the convert and test tensarity.py. It has some command line arguments which you can see here. The command line arguments are the ORNX file, the floating point precision, the batch size, and the file name in which the result should be saved. So let's see how that works. I believe it's in client. So this file is copied over to the system under test, and then using SSH we can execute this file remotely. So the first thing which it does is it will construct the tensarity engine if it's not already constructed from a previous build, and then it will test the engine by using the script over here. So we have a function do synchronous inference. You can find it in trtinference.py, and this will basically just pass a random tensor and random numpy array to the neural network, and then it will time how long each of these operations take to execute using the line profiler utility. Once the number of iterations, 100 by default, are done, the results are saved in a dictionary. So we save all these pieces of information to a dictionary, such as the batch size, the platform, and the precision, and then we save the dictionary to a pickle file. So once that is done, once we've created that pickle file, we can go back to this, and what happens after creating the pickle file is that the pickle file is then copied over to the benchmarking server. That's done using sftp.get. So this is used for copying over the pickle file. So we are essentially using SSH for getting all this inter-device communication done, and the output of that SSH can be seen over here in this text area, where it shows the output of each line of code in std out. Alright, so the second thing which I'd like to show is the validation format. So the concern with validation is that each neural network provides a different output tensor, and sometimes you need some post-processing to actually use that output tensor and to get a result. So that is why the way validation is done using this project is by creating a validation zip file. So in this case, I have this lanenet validation.zip. The source of this can be found over here, and the way this works is that we have a script validate.py which is automatically run by the benchmarking server. So this is copied over to the system under test, and then it's executed remotely using SSH, just as we had done for the benchmark. And the essential part of this is that it should save a pickle file to disk, which contains the accuracy, the platform, like Tegra or the x86, and the model, which is the the TRT file name in this case. And those results are saved to the command line argument, the second command line argument, sys.argov2. And once the pickle file is saved, we go back to this file here. So the pickle file will now be on the system under test, and we need to get it back to the benchmarking server. So for that, we use sftp.get. So to summarize, the scripts which are run on the benchmarking server include utils.py, benchmark.py, and dashboard.py. And everything else, such as the client scripts, so all the files in the client subdirectory and all the files in the validation subdirectory, are all run on the system under test, and we do that using SSH, using this command over here, ssh.exec command. So ssh.exec command returns file descriptors for both std in and std out, You don't need stdin, so you can close it if you want to. But for std out, we actually get each character and then we buffer each line, and then once the line is done buffering, we then use a WebSocket for showing it over here. So this is how we're able to get the output of std out live in the text area, which you see over here. Okay, so that is how the overall flow of the benchmarking utility works. If you go to the GitHub of this, you can see the model conversion procedure. So how this all this started. So we first take a TensorFlow frozen checkpoint, we convert it to a frozen model format, then we convert to an ORNX using TF2 ORNX utility, and from that ORNX we convert it to a TRT on the system under test, or we convert it to an OpenVINO file also on an Intel system under test. So this is the overall flow of how all these things are happening. So for this project, it's expected that the ORNX file is already available, and the only steps which are taking place are this TRT conversion and the OpenVINO conversion on the system under test. Yeah, so this concludes the presentation and how the benchmarking utility works. Thank you for watching.